Hi, this is Dan Buller, retired electronics engineer, sitting on the front deck of my house. But again, I want to try to get through DAC testing for the Nextest DSP training course. Try and get through it. I think this is episode 7. So here's some DAC testing basics. Here's a simple voltage out DAC. It's a real simple negative feedback op amp, and if you watch my op amp video, you'll see right away how this works. It generates a voltage based on the input value, 1 or 0, just ones and zeros. You can pick voltages if you want, but just ones and zeros, where the top input is the MSB and the bottom input is the LSB. And so that's a simple DAC. That's how DACs work. Common problems with DACs. Offset error. The all zero output value is not the right value. That's a common thing. Gain error. The difference in the output between all ones and all zeros is not what it's supposed to be. Poor linearity. Resistor mismatches cause some bits to have more or less weight than others. That's where nonlinearity comes from, and we know that that is what creates harmonics in a DAC. And glitches. Some parts switch faster than others, and in the case of like video DACs, we call them sparkle codes because they make little sparkles on the screen, and we don't want sparkles on the screen. I mean, you're paying good money for a TV that doesn't have any sparkles in it. Back in the old days, that was a problem. Not today though. Offset testing procedure. So to test the offset, you set the input to all zeros, measure the output, save the results for gain testing, subtract the ideal zero value from the measured value. Boom, you're done. Gain testing procedure. Set the input to all ones, measure the output, subtract the offset. Now, nonlinearity. Nonlinearity can be measured indirectly via THD, IMD, or directly. We've talked about total harmonic distortion. IMD is intermodulation distortion, and I have done a video on that, so let's not go there right now. DACs are often tested for 2 types of nonlinearity: integral nonlinearity, INL or ILE, and differential nonlinearity, DNL or DLE. Here's what integral nonlinearity looks like. It has the steps and it's following the right path from zero offset to maximum gain, but it's not following a straight path. It's following a curved path, and that you don't want. So that's integral nonlinearity. DLE, that's a little more subtle. That's differential nonlinearity. That's where the steps are not all the same. If one step is bigger than the other or smaller than the other, that's differential nonlinearity. Here's a serious DLE error, or differential nonlinearity error. This is called non-monotonicity. It's hard to say. Now, it's interesting, the root of this word, non-monotonicity. What the hell does that mean? It means that if you put a single tone in, you won't get a single tone out. It doesn't give you a monotonic waveform. It doesn't give you a single tone because it generates harmonics. What a shock. You may recognize this. Here the waveform is stepping up, stepping up, stepping up. Then it steps down a little bit, and then it steps up hugely in the transition from 3F to 4-0. That was actually a real problem caused by a glitch. It wasn't really nonlinearity. It was a problem with a glitch at the 3F to 4-0 transition. Non-monotonicity happens when an increment in the input code results in a decrease of the output voltage or current. Any DAC that specifies less than 1 LSB of DLE is by definition monotonic. As long as the output voltage always goes up with the input value going up, then it's monotonic. But if the input goes up and the output goes down, that's non-monotonic. If a DAC appears to be non-monotonic, the error may actually be due to a glitch. Oh, it's somebody. Some big-ass tug. He's coming close, too. Renee. Okay, so here's a DAC going along, and the input codes go from 000000 to 11111, and it's supposed to go up all the time. And so we're just basically going to generate a ramp. And there's a number of ways to generate a ramp. Back on the Nextest, had an algorithmic pattern generator. And I saw on a Japanese tester when I was in Taiwan, they had a Japanese tester that generated the ramp using an APG. I'm like, oh, that's a great idea, because I love APGs. And not everybody who knows mixed signal knows anything about APGs, because memory testing and mixed signal testing are kind of like different things, right? People don't mix those things. Well, I do, because I've done them all. So I've done memory testing, I've done DAC testing, ADC testing, pretty much everything. Okay, so here's a DAC test setup. Here we have the DUT, that's the device under test. We have the digital pins coming from DBM. What's DBM? Data buffer memory. That's something called data buffer memory on the Nextest. And that's basically a memory where you can store data of any kind. So if I just store a ramp in the data buffer memory, that would do it. I could use the APG, algorithmic pattern generator, or I could use vectors, just plain vectors. So that data goes into my DAC. The DAC, which is the DUT, puts out an analog waveform, and we're going to capture it with our ACI. That's the analog capture instrument, which is a 14-bit A to D with 256K of waveform memory, and the clock generator. Now remember that the digital that is driving this is controlled by a clock, and the clock generator to the ACI is related. It doesn't have to be the same frequency, but it's related. Okay, here's a cool way in the Nextest to create a ramp waveform for testing DAC. You say waveform temp 0, wave generate DC, object 16 samples at 50 megahertz sample rate, 0. So we're generating a 0 volt DC offset. Waveform temp 1, waveform generate DC, object 16 samples, 50 megahertz sample rate, generator 1. And then the next one, waveform ramp gen 2, waveform generate ramp, object 256, 50 megahertz, 0 volts to 1 volt, waveform concatenate, object temp 0 to object, and waveform concatenate, object temp 1. And that generates your ramp. So what it generates is this right here. So it generates 16 samples, 0 volts, and then it generates the ramp, and then 16 samples of 1. And why do we do that? Because we know that when that thing goes from all ones to all zeros, it's going to create a big glitch. And we don't want to capture the glitch. That's a bad thing, because it will cause us all kinds of grief. First time I tested a DAC, I had a really big problem. I think I was in Taiwan, and I had to call Paul Botsford. He was at Semicon in San Francisco at the time, and I was able to get a hold of him finally, and I said, hey, what's going on with this? He says, okay, you've got a glitch there. Move your sample. That's all you got to do. Move the sampling point a little bit away from where that ramp goes straight down to 0, and then goes up to 1 and 2 and 3. So when that thing drops, you get a big glitch down there. If your sample point is right there, you're screwed. So, and that was the problem. That fixed it. So Paul Bosford actually helped me once. Nextest provides 2 functions to test DAC linearity. You know, I used to do this manually on the Vista and on the STS 3000, and I can still do it, but I don't have the tools right now, and I don't have any of the other course material to show you. But it's really cool. It's really fun and easy to do. But David wrote functions for it. So there's waveform, DAC, ramp, INL, DNL. You give the waveform. It gives you 2 waveforms waveform out INL and waveform out DNL. So you give it two waveforms to put the INL and DNL waveform into. And it gives you the double INL and double DNL. And then it gives you a choice of methods. And the line fit method defaults to adjusted fit. Okay, also there's DAC, ramp, INL, DNL. You give it the input waveform, and then it just returns INL and DNL. These are pretty good. These are great little functions. But doing it is really cool. I mean, doing the DNL and INL yourself is really fun. Well, fun for some people. Okay, here's an example. ACI get waveform, capture one, that's the ACI that we're asking. You can have multiple ACIs in a Nextest. You can have up to 4, I think. ACI get waveform, capture 1, 0, captured. Captured is the wave. So you pull the waveform out of the ACI, and then you do waveform DAC, ramp, INL, DNL, captured, blah, 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 and you're good to go. So that's how you test a DAC. And there's a lot more to it, possibly, you know, if you don't have Davers functions, but I can't tell you about that because I don't have any tools for that. Okay, I mentioned in another video the glitch testing. Glitch testing is an issue. Just like memory addressing problems, glitches are likely to occur at major carry transitions. To see glitches, you have to equivalent time sample, that is undersample, with your analog instruments. Glitches are very short-lived. You have little chance of seeing them even if you sample very fast. Glitches are measured by their energy. Energy is measured in volt-seconds, the products of voltage and time. So that's volt-seconds, and I made a video about volt-seconds. Pretty funny. Here's a glitch. I found this when we tested our first DAC, which was a DAC in a Philips microcontroller. And we did this test on this microcontroller. It had DACs and ADCs. And the ADCs went pretty good, but the DAC test had this big glitch in it. We thought at first it was a DNL problem, but it was a goddamn glitch. And so here we have the DAC is putting out 3F, and then it goes to 4-0. When it goes from 3F to 4-0, whammo, you get hit with a glitch. And so that's an issue. Here's a good look at the glitch. What we're going to do is measure the energy of the glitch. So we have to cut it off somewhere near the top and then measure the total energy. Yeah, it's Saturday, so people are out having fun. You know, that's the great thing about living on the river. You get to see a lot of people having fun. You can have fun too if you want, or you can just watch the other people have fun. It's a lot cheaper that way. Okay, here's our glitch energy test code. We set something, it's a double, called mean value. Mean value equals a waveform arithmetic mean captured. So that's a captured wave. So we're taking the mean of the captured signal. Waveform clip upper, temp wave captured, mean val. So we take the mean val, we find the mean val, and we clip the upper to clip off the upper part of it. Waveform subtract temp wave mean value, so we subtract out the mean value from the temp wave. Waveform multiply it by -1. Waveform subset glitch temp wave, glitch start, glitch stop minus glitch start plus 1. Glitch energy equals waveform sum glitch times waveform get increment glitch. Okay, so what did we do there? We multiplied the voltage times the time. That's what a volt second is all about. You multiply the voltage times the time. We know the time because that's in waveform get increment. And we got the waveform sum by doing waveform sum on the glitch. Output glitch energy is %3.3 F nanovolt seconds. Glitch energy divided by basically 1 nanosecond. So here we are measuring the glitch energy in nanovolt seconds, and basically it's the multiplication of voltage and time. That's all it is. Doggy barking. We have neighbors. And that's the manager, so we don't say too much. Anyway, so it's a lovely Saturday, so I'm going to get going. So that's DAC testing. One more to do, that's ADC testing. So once again, from the river, this is Dan Bullard.